Now we're going to look at a lemma that says if you have an affine variety, then this affine variety is a noetherian topological space. So let's write this down. Every affine variety is noetherian, meaning you cannot have an infinite descending chain of strictly decreasing closed subsets. This was the definition of what it means to be noetherian. So let's prove this. Oh, I'm writing Beweis, but I want to, of course, write proof, since this is supposed to be a video in English. We're going to do a proof by contradiction, meaning we're going to assume that we have an affine variety. Let's call it X. So every affine variety X. Every affine variety X is noetherian. So suppose X is not noetherian. Let's abbreviate this by big N, which means there is an infinite decreasing chain, a strictly decreasing chain of closed subsets in X. So there is X0 strictly included in X1, which is in X2, and which is in X3, and so on. So this is this strictly decreasing chain. And now if you apply the operation I to this chain, so meaning you look for every closed subset, xi, you look at the ideal of this closed subset, you get a strictly increasing chain of ideals. So you have I of x0 is strictly contained in I of x1, and this is contained in I of x2, and so on, right? So this is, since we have this inclusion reversing relationship here. So if you have a chain, if you have a strictly decreasing chain of closed subsets, and you apply this inclusion reversing operation, namely I, to this chain, you get a strictly growing sequence of ideals. But now remember, we have the Hilbert-Nullstellensatz. I mean the Hilbert basis theorem. So by Hilbert basis theorem, we know that that the ideal that you get when you look at the union of all these ideals in this chain. Yeah. So maybe I have to write this down first. So I'm talking about this idea here. So I is the union and ranges from 0 to infinity of the ideals I, X, I. This is an ideal, as you can easily check. And now the Hilbert basis theorem tells us that this ideal is finitely generated So we have a finite set of generators, so we can write I as generated by polynomials f1 to fn. And of course, all these polynomials have to lie in one of the ideals. And since this is this one here again is an increasing sequence of ideals, all these polynomials have to lie in the same ideal. So all of them have to lie in all fi, where I ranges from 1 to n, are elements in, let's say, I of xm. And now look what we have, because we are approaching a contradiction, which is of course what we want. Now what we have is I, which is the ideal generated by f1 to fn, is contained in I of xm, but by this assumption here again, I of xm is strictly contained in I, since we are talking about a strictly increasing sequence of ideals, and this is of course a contradiction. And this means that we cannot have such a strictly increasing sequence of ideals here, and this in turn means that we cannot have this strictly decreasing sequence of closed subsets of our variety X. And yeah, this concludes the proof.